Okay, so very nice to be here, and I'm going to talk about surface objects procedures, integrating learning and graphics for 3D scene understanding. So as you can see from the title, we want to understand, if we want to solve scene understanding problems in computer vision, should we just use, a pure machine learning data-driven approach, or is there any knowledge in the physical world, especially those used in computer graphics, right, surfaces or object representations, or even procedures? And can any of them be integrated into learning systems to make learning systems maybe more efficient or perform better or more generalizable? Okay, so to begin with, this is really joint work with many of my collaborators. Xiaoming Jiang, Zhou Chongzhan, and Jerry Ma, both all PhD students at MIT, and Yikai Li was a visiting undergraduate student at MIT. And Josh Tenenbaum and Bill Freeman, my advisors, and Noah Snavely, I worked with while I was at Google Research, and also supported by all those agencies, including Samsung, through the Samsung Fellowship. Okay, scene understanding. When we say we humans understand the scene, what do we really mean here? If we look at this picture, you probably looks very familiar to you, like there were roads, there were cars and trees and buildings. But when you say you understand the scene, you not only recognize these semantic pixels, but you can also easily, use your knowledge or understanding of the scene to answer questions, such as how many cars are in the scene. There are probably like 4 or 5. And what's the color of the closest car? Black. And also, you have a knowledge that cars are in 3D, the scene is in 3D, and cars have 3D geometry. So you can say, how would the car look like from the front? And using your prior knowledge of the 3D geometry of the car, you can probably imagine that. As well as what is going to happen. Right? It looks like, the one who took the picture is also in the car. So what's going to happen is most likely, the person is going to move forward, and also the cars nearby are going to move forward as well. Okay? And what if it's raining? So it's not only about objects, but also about the scene parameters in general, right? How would the scene look like if it's raining? And this not only applies to the objects that you've seen before, you're familiar with, like cars, trees, and buildings, but also to novel objects, right? Here is a pile of toys, and some of them you may be familiar with, but some of them you may have never seen before. But you can also easily answer, similar questions to these novel scenes, and your knowledge of scene understanding, your ability to understand scenes also applies to novel objects. So I guess, one very important question that I want to answer in my research is how can we really build machine scene understanding systems that are flexible in general, so that you can have knowledge to answer all these questions. Okay, but to begin with, maybe let's look at a simpler case. That is, if we now given an image or a scene of a single object, and you want to just understand the 3D geometry of the object, right? So we know that the sofa, it has 3D geometry. It's not only just like pixels. And we can imagine how it would look like from the back. So I guess the very first problem we'd like to understand is, can we actually infer the 3D geometry of the object from the image? And to connect 2D image and 3D shapes, there's one direction, that is the perspective from computer graphics, right? That is, an important subject in computer graphics is rendering. That is, if I'm given this 3D shape and textures and viewpoints and lighting, and how can I render the picture of the object? And the other direction is, computer vision. That is how I can reconstruct the 3D shape from 2D images. And that's also more or less why computer vision is sometimes called vision as inverse graphics. And in the past, people have relied a lot on graphics cues like surfaces and shadings, to recover the shape. But now when deep learning comes, when people say computer vision, it's more like I have a huge giant deep network, and I just took this image and magically it just produced a 3D shape. And in many cases, especially in cases where the output is, or the labels are unambiguous, and you have a lot of data, a lot of compute, like image classification, this kind of approaches works really well, black box approaches. But for more challenging problems, more flexible general understanding that involves geometry, is there any knowledge we can take from computer graphics, right? When we are building these deep learning systems, can we make them a little better or more generalizable by taking representations from computer graphics? So this is a question that we'd like to answer. And to do that, let's first see how graphics or rendering works. So again, this is like an extremely simplified version of how it works. the forward process going from 3D shape to image to 2D image is like image formation. And how it works is you have this 3D shape, you put it in the 3D space, and there's maybe a light source, and it sends rays to the objects, and it hits the visible surfaces, and the rays get reflected into the camera. In front of the camera, there is an image plane, and that's why you are seeing the object in the image. But we are really seeing from the image. It's not a 3D geometry of the object, right? You're seeing the visible surfaces of the object. So, for example, one of the legs is occluded in the image, and of course we know chairs has 4 legs, so you can imagine there should be a 4th leg. But from the picture, you're not really seeing it. You're only seeing the visible surfaces with 3 legs. And therefore, maybe you say, okay, if this is like a simplified model for image formation, then if we want to solve the inverse problem of estimating 3D geometry or shape from 2D images, maybe we can also design a system that works accordingly in 2 steps. The first step is you take the image, and then you try to estimate the visible surface. And one way of parameterizing the visible surface is to treat them as a depth map, right? So you can see that the depth map, every pixel is representing how far that pixel is from the camera, is a parameterization of the visible surface. So what if I design a system that first do depth estimation, going from color to depth, and now you have the visible surface. And the second step is I do shape completion. That is, I go from this depth map, and then I try to complete the 3D geometry of the object using the prior knowledge. Because once I have the depth or the visible surface, there's no more information that input image can provide me, right? Because everything I can see or understand about the geometry of the object is already encapsulated in the depth map. And everything after that, I have to use learning. I have to use my prior knowledge of what shapes or chairs look like to complete it. Right, so the second part is not really about pixels; it's about my prior knowledge. It's a learning problem. While the first part is more like an inference or estimating visible cues, right? The visible surface. So to realize that, it's a very simple idea. Now we have a system that instead of having an end-to-end neural network, we have 2 smaller neural networks, modular neural networks. The first one estimating depth, the second one estimating 3D shapes. And if you train such a model on ShapeNet, right? It's like the large shape repository of 3D CAD models, and you can take shapes from ShapeNet, put them in front of random backgrounds and render them so that you get images and shapes for training. And if you train a model like this, the 2-stage model on ShapeNet, instead of compare with the 1-stage model, then it's surprising that you can actually see a lot of improvements. So you train on ShapeNet, synthetic images. Now you test on real images like these. The chairs is actually quite challenging. If you just do end-to-end shape or prediction, this is what you get, where you get roughly the chair shape, but you lose a lot of the details. And by having depth map or visible surface as an intermediate representation and design a 2-stage approach, your output just looks much better, right? Because here, by putting surface as intermediate representation for learning, the system now learns to focus more on what really matters to our perception in the reconstructed geometry, that is surfaces. I really want to get a surface right. And by putting surface into it, it also helps me to do better. And here are more results. Right? Again, the system that representing or modeling depths or visible surfaces really gives you more details. So this is actually a while back, right? Back in Europe's 2017, where we did it with Yifan Wang, who was also a visiting student at MIT and now is a PhD student at University of Washington. Okay, you can see that it's a very simple idea. Just by taking intermediate representation from computer graphics, really already allows you to reconstruct the 3D geometry much better from the 2D image. But we said at the beginning, our ability to understand 3D scenes also generalizes to novel objects, even to objects that we've never seen before. But how would this model or any other 3D geometry estimation model perform on unseen object classes? So we did a simple test. You take models and train them on chairs, planes, and cars. These are the 3 largest categories in ShapeNet, right? So these are like the categories that you have the most CAD models for. And you can generate all those training images, and now you test it on a table. A table is also probably the 4th common object categories in ShapeNet. And tables and chairs, they're both like furniture, so it's not that different. It's quite different, but it's not that different. And if you take a test image from the table and you send it to the network trained on chairs, planes, and cars, and this is what you get. Okay? So does it look like a table? It looks much more like an airplane, but it more or less looks like at the top of the table, right? But why is this happening? Because the network figures out that, okay, what is this? I've never seen it. And I should probably try to just retrieve a nearest neighbor from the training set. And what would be the nearest neighbor for chairs, planes, and cars if I'm given a table? Well, the top of the table does look like a airplane a little bit, right? Because it's very thin and it's like round, and sometimes airplanes can be like that. So I just try to retrieve a similar airplane. And so this shows the network is not really learning to reconstruct geometry, but it's more like smartly retrieving nearest neighbors from the training set. This is not only a problem to our approach, but this is a common problem shared by many other papers. The field of single image 3D geometry or 3D reconstruction, it's been very popular, and people design all those approaches for using point cloud, voxels, meshes, multi-view images, and this is a common problem for all these approaches. And for people who are interested, there's an interesting paper from Vlad and Colton and Tom Sprock's group in CVPR 2019. They call it, "What do you single view 3D reconstruction networks really learn?" And they have a more in-depth analysis of this problem. Okay, so how can we solve that? How can we really build a model that really generalizes to objects from categories that we've never even seen before? And we said we want to take inspiration from computer graphics. And let's see what is really happening here, right? Especially in the second stage. So you go from images, you go from image to a depth. And depth, is parameterizing visible surfaces, but it still is a 2D depth map. But here, the final output is a 3D shape. So there's a 2D to 3D projection going on, right? Essentially, the second network is doing this projecting depth into 3D, projecting this 2D depth map into a 3D visible surface. Well, we already know this process is a deterministic and also fully differentiable process, because computer graphics, this is perspective projection. You can write it down as equations. It's fully differentiable. So it shows that the second network, the shape completion network, is really over-parameterized. It's learning this deterministic mapping, which it doesn't really have to learn, because we can just write it down. It's universal, and we already know about it. It's building into any graphics rendering engines. So then our idea is, if we already know it, we can write it down as differentiable. Why don't we just build it into the system instead of having the network relearning the whole thing? Right. So now the system becomes, I go from an image to estimate the depth, and then I have a differentiable back projection module that back project the depth into this partial or visible surface, as you can see here. The fourth leg is missing because it's not in the visible surface. And then the second network, shape completion network, really just focusing on completing or the 3D shape. So then this very simple idea, right? Again, you have this visible surface, and you have putting surface as intermediate representations to help learning. And this very simple idea combined with this explicitly written back projection module, and you take the models and train on chairs, planes, and cars, and test it on the table. This is what you got before, direct prediction we call, and this is what you get by modeling both depths or surfaces and the projection. So of course there are still all those artifacts, and but this shape looks much more like a table compared with the original input, right? Because by building in depth and projection, the network no longer has to learn these equations that are universal and known and deterministic. And if you ask them to learn, they will learn it only for the training object categories, that like chairs. But if now you're no longer asking them to learn, and you're just building this into the system, and now they can focus on learning things that are more generic or more universal across object categories. That is, how can I complete the shapes? And this really allows you to get much better results, even for objects from unseen object categories. Okay, but if you still, if you look at the top of the table, then you see there's all those roughness going on, and which is not really, the bumpy surface is not what we want, because we have a pretty strong prior from the input that at the top of the table should be quite smooth. But why is this issue happening? This is because the partial surface or visible surface in 3D is really sparse, right? Because essentially, it's like a 2D got projected into 3D. So its occupancy in the 3D space is really sparse. And for the shape completion network, if it's purely operating in 3D like voxels, then it will be hard for the completion network to capture surface features. It will span all those expressiveness or representational power in the empty spaces, for example. So how to let the completion network to focusing more on the surfaces to really get the results much better? And this example, it may be like it's okay, but I can show you a different example where I give you a chair, and this is output of a chair, which looks pretty good from the input view. But if you rotate it, then you see, okay, this is definitely not what I want. It's not like the completion network is doing nothing. It's doing something. You can see it's roughly a chair. It just doesn't have the notion that object surfaces need to be smooth. It's not really focusing on getting surface to be right. So how to build a network that focuses really more on surfaces? Our idea is to introduce spherical maps as a surrogate representations for surfaces in 3D. So what is a spherical map? You have this visible surface or object in 3D, and then you put it into a unit sphere, and then you can send rays from the surface of the sphere to the object, to the center of the sphere, right? And then you record for each ray how far it has traveled until it hits the object, right? So you can parameterize the rays by azimuths and elevation. So you can parameterize like a UV mapping, right? You have the azimuths and elevation, and you parameterize all the rays. And then for every ray, you record how far it has traveled until it hits the object. And this gives you the spherical map. And the interesting part about a spherical map is you can see that every point or every pixel in the map really corresponds to a point or on the surface of the object. Right? It's no longer representing or concerning about the object or like 3D space, especially the empty spaces. It's really focusing more on the surfaces. So if you build that into the system, now you have the depth map. But instead of I back project it into a 3D space with the visible surface, I back projected into a partial spherical map, right? And then for the shape completion network, what's its job? Is now you have an image, you first estimate the depth, and then you back project it into a partial spherical map. And then the completion network just focus on, in paint or complete the partial spherical map to make it a full spherical map, right? So you're converting the problem of shape completion into an in-painting problem. And this, as you can see on the left, is a partial spherical map, and hopefully on the right, you can see there's a full spherical map with the completed visible surfaces. No, it's now from visible surfaces to full surfaces. And for spherical map, there is a limitation. That is for every ray, because you only record the first time it hits the object. So, it cannot really represent self-occlusion, right? So there are parts of the object that are not captured in a spherical map because of self-occlusion. If I visualize it, you can see it's roughly capturing the entire shape. But for things like the chair back that has some thickness, the front of the chair back is not really captured. Okay, so to solve that, we eventually added a small neural network, just to call it like a refinement network to deal with the self-occlusion problem. Okay, so here you're introducing another representation, spherical map representation, to really hope the system can focus more on the surfaces, which is what really matters, in computer graphics, but also really matters to human perception. Okay, now by having this final system, if we take a model that trained on chairs, planes, and cars, again, you test it on this table. This is what you get before, direct prediction, and without spherical maps and with spherical maps. And you can see, although the geometry is more or less similar, or they both look like a table, but with spherical map representation, the output, especially on the surfaces, tabletops, are just much smoother, because now the system learns, okay, actually really focusing on getting the surface right. Okay, so we named this system Generalizable Reconstruction, or genre, and this was published in actually now 2 years ago, in Europe 2018. And as I said at the beginning, Xiaoming Zhang and Zhoutong Zhang, they're both PhD students at MIT, really contributed most significantly to this project. Okay, because we call it generalizable, right? So we want to show the results on generalizing to unseen object classes. Now, everything here, again, is trained on chairs, planes, and cars. But now I tested not on the table, but also on the bookshelf and the sofa. And here are some results from the baseline. And the baseline is trying to represent shapes or output as a collection of surfaces. So this is like a collection of surface representation. The baseline works really well on the training object categories. But for unseen object categories, it doesn't do that well because it's trying hard to retrieve nearest neighbors from the training set. And this is our method, the genre. Still, you can see quite some artifacts, actually. But it does look much better compared with the baselines, and you could compare that with ground truth as well. So for example, for this sofa, where only the visible surface is only about the front, right? So, but our model can successfully complete this back. And remember, we have never seen a sofa. All we have seen is like chairs, planes, and cars. So how could it do, right? How was it able to do that to complete the back of the sofa? That is, you can, if you visualize or the predicted partial spherical map, then you can see that the non-visible part, the back of the sofa in the partial spherical map or single view spherical map is just like missing values. And after this shape completion network, as we said, which is really painting the spherical maps, and the output you get is like a full or multi-view or omni-view spherical maps, really capturing all the surfaces, including those that are non-visible, and you can see the missing values, and the originally non-visible pixels or surfaces, are now painted, and also painted to be smooth, right? So then you can convert from this multi-view spherical map back to the completed shape. And this is really what you get. Some more results. Again, trained on chairs, planes, and cars, but you tested on beds, tables, and benches. And you can see, especially for the bench, it's very clear that the baseline is trying to retrieve an airplane to explain it. But this is our output. Again, it's not perfect. You can see there's a missing leg of the table, but it also captures some of the details, like on the bed and as well as the leg of the bench as well. And you can compare that with ground truth. Still a lot to do, but quite some improvement already. And finally, we also tested something a little more crazy. That is, if we train only on chairs, planes, and cars, can we really generalize even to non-rigid object classes like humans and horses without seeing only chairs, planes, and cars, right? By only seeing chairs, planes, and cars, can we generalize to humans and horses? And this is our output, and this is the ground truth. Far from being perfect, but it's interesting that the system has learned the surface needs to be smooth, the object needs to be complete and closed, and therefore from a single depth map here, you're actually able to complete depth map and give you the estimated geometry of humans and horses. Okay, so here we have shown, how a very simple idea, but very important idea, that is surfaces in computer graphics, as well as projecting, how 2D surfaces, how surfaces are represented in 2D as a depth map and represented in 3D as a visible surface, and how they can be, projection and surfaces, how they can be integrated into learning systems to make it work much better, but also more generalizable. This is like this 2D to 3D direction, and there's a pioneer in, I would say, computational neuroscience, but also computer vision called David Marr, and he has a theory of human perception of 3D objects, which is, in some sense, could be controversial, but he has this important notion called 2.5D sketches or 2.5D surfaces. That is, how the role of surface plays in human perception or in human understanding of 3D objects. And here we also see how they can be integrated into a learning system for 3D shape reconstruction. But now let's look at the other direction. That is how 2.5D surfaces can be used as intermediate representations, not only for reconstructing 3D shapes, but also generating better 2D images. Or what does that mean? That is, if I want to, we have known that in computer graphics, if I'm given this 3D shape and textures and lighting, I can render beautiful pictures. But what if I want to synthesize new 3D shapes? What if I want to synthesize objects with different texture, right? So in the problem of shape and texture synthesis, we try to understand how the role of 3D shapes and 2.5D surfaces and 2D images. And really a while back, in 2016, Chen-Kai Jiang, who was an undergrad and master at MIT, worked together on extending this very well-known popular generative adversarial networks from 2D to 3D, so that you can synthesize 3D shapes instead of 2D images. And this is what you can typically get from a 3D generative adversarial networks. And later, together with Zheng Yan, who is the first author of CycleGAN and many other influential papers, he graduated from Berkeley and moved to MIT as a postdoc. Now he's an assistant professor at CMU. But while the time that he was a postdoc at MIT, we worked together with Chen-Kai and a few other people to think about how to extend this 3D game model to also generate 2D pictures. And the idea is kind of very similar to what we introduced before, but now you're doing it in the other direction. You first have a 3D GAN, you get 3D shapes, but then you do a forward projection. You take the 3D shape and condition on the viewpoint, you can do a forward projection, and you get a silhouette as well as a depth map. And then you can go from the depth map to generate a 2D image. And this part, the second part, the texture network, is like a conditional cycle GAN. Right? So you're doing image translation, converting this 2D depth map into a 2D image. And by doing this, you can not only synthesizing 3D shapes, but also synthesizing 2D pictures of those corresponding 3D shapes. And this also brings an additional benefit. That is, it's almost impossible to get very high quality data of both 3D shapes and realistic textures. But you do have a large data set of 3D shapes that is ShapeNet, which you can train on it to generate realistic 3D shapes. You also have almost infinite images of realistic cars, right? 2D images of realistic. If you Google search cars, you get so many cars. So while it's impossible to get paired 3D shapes and 2D images, you can get unpaired 3D shapes, which you use to train 3D GAN, as well as a lot of 2D images, which you can use to train, you can segment them so that you get a silhouette, and then you can use that to train the texture network. Right? So this also relieves our burden on getting the right training data, but also allows you to train 3D shapes and go through a differential projection and through a cycle GAN to get 2D images of these 3D shapes with realistic textures that you learn from real images of cars using cycle GAN. This also gives you a disentangled representation of, you can see there's a texture code, a viewpoint code, and a shape code. So then you can do very controllable image generation and editing of the viewpoint, shape, and textures. For example, I can keep the code of shape and also the texture by just change the viewpoint. Or I can just change the shape, but keep the viewpoint and texture. Or I can just change the texture, but keep the shape and viewpoint. I can do that for chairs. I can do that for cars as well. Changing the viewpoint, changing the shape, changing the texture. I can also do interpolation in the latent space. I can keep the viewpoint and the texture by just interpolating between two shapes. I can do the same for interpolating textures. Or I can interpolate in both. Right? I'm keeping the viewpoint, but I'm interpolating between both shapes and textures. You can also do transfer shape and texture. For example, if I've synthesized all those shapes of 3D cars, now I see, okay, I have these beautiful pictures of cars that I took from the internet. Can I imagine how the car will look like, those synthesized shapes will look like if they're given the texture I took from the internet? And you can take the texture code and apply them to the cars you synthesized and imagine how they will look like, right? You can transfer the shape and texture and to do some combinatorial generalization. So by integrating learning and computer graphics, here you're having this is, I would say, it's a hybrid graphics rendering pipeline, right? You still take, the main, I would say, notions or important elements from computer graphics. That is, it's important to get 3D shapes. It's important to get surfaces and projections and textures. But then the way you realize them is to replace them with neural network or data-driven methods so that you can do it in a more flexible way. I can just take textures from your images I took from the internet. Well, while it's very hard to specify a UV map for textures, I can take it from the internet. I can synthesize new shapes using, again, by learning from a large shape data set. Right, so by taking the notion of surfaces, again, from computer graphics and integrated with learning, then we have shown we can do much better in both the inverse graphics side, reconstructing 3D shapes, but also in the forward graphics side, in synthesizing shapes and textures. We can also extend that to scenes. So I'm going to go pretty quickly here, but the main idea here is pretty simple. That is, we've shown for the cases where there's a single object, how can we really infer the textures and geometry and viewpoint of the object. But now if I have multiple objects, right, and can I just do that for every object separately? But also because scenes, there are things that are not really objects, or maybe they're objects, but it's really hard to separate them, like trees and skies and roads. So I also have a background semantics map, right? So you can see I try to infer the scene and build, I would say, a semi-interpretable representation for it. That is, you have a set of objects, there are categories, but there are also poles and the texture. And you also have some segments for the background, like skies and trees and roads. Okay, so then you can do the thing we did before, that is, what if I change the viewpoint code? Or what if I change the position code of the object? So here you can move the cars to the right. And now you can apply the augmented or the hybrid graphics rendering pipeline we said before. Right? I can take the shape, but now with the different positions, and I send it back into this hybrid rendering pipeline to resynthesize how the scene will look like, and do forward graphics. Now it's here in the output picture, everything is the same as the input picture, except that the pose or the position of the car has been changed, and they all move to the right. So this is joint work with Shenyu Yao and Harry Xu, they're PhD students at MIT and Princeton. Again, we're building this disentangled representations. And the bottom two rows here, as you can see, is texture. We call it texture derenderer, geometry derenderer, but it's really just getting texture code and also the pose, the geometry code and the viewpoint, the pose, right? The only thing you changed or you added into this scene extension model to scenes is you also have a semantic map estimation just to deal with background that are not really objects, skies and trees and roads. And then you put them as an additional channel of input into your hybrid or re-rendering pipeline. So you can get results on virtual kitty. So here's our original image. I can see there's a car that is a little far from me. So I was like, okay, how would it look like if I move it closer? So I can change the car, the position of the car to make it closer and closer and closer. And this is the output. Of course, this, there's only that much signal, right, in the input image of the car. So the network has to use the prior knowledge to imagine, okay, how will the car look like, from these signals, and how can I really make it more realistic when I move closer? But here is the output of edited images. And because you have this very flexible, interpretable, disentangled representation for object poses, positions, but also colors and textures, you can say, I'm changing the position in the first row, but in the second row, I want to change the pose. So how would the red car look like if I rotate it to the other direction? And every other, the attributes of the other objects as well as the background is not changed. And in the third case, I was like, okay, what if I want to change the texture or the color of the car? Or what if I want to change the weather? How would the scene look like if it's raining? And the final example, I'm like, if I have a car, and then I think it's kind of I want to remove it, right? How would the scene look like? Because we understand there are objects made, the scenes are made of objects, and objects have their own 3D geometry and 3D positions and texture. So I will know if I remove this car in the front, then the car that was originally occluded should now review, and I should complete the car, right? By understanding its geometry and putting texture on it, right? So this is what you can do by having this, graphics-based, but 3D scene understanding system that if I remove the car in the front, I can see the back car is now reviewed. I can remove a few more cars and how the scene will look like. Here are some more results on the CityScape dataset, which is a real data image dataset. Virtual kitties are synthetic images. And CityScapes can do similar things, right? If I move the car a little closer to me, closer to me, closer to me. And here you can see the results are not as good, probably because real images are just much more challenging, and the distribution of texture and appearance is more diverse. But it's roughly doing what we want, right? Moving the car closer, and it's roughly realistic, I would say. And in the second row, again, what if I want to move the car, the pose of a car, to rotate it to the left, to the right, to the side? In the third row, I'm like, if I have a car, this is a very first picture I show. And if I have a car that is partially occluded, what will happen if I move to the right, if I move it a little closer, and if I move it to the right? So you can synthesizing or editing things like this by understanding objects, by understanding the surfaces. Okay, so here we have shown up to this moment, right? The role of surfaces, especially, but also the role of objects, right? Having an object-centric representation about their geometry, about their pose and viewpoint and texture, and also for every object, by having surface as intermediate representation for reconstructing their geometry. What's the role of surfaces and objects? Both are very important notions from computer graphics rendering pipeline. How they can be integrated into especially an inverse graphics system for scene understanding and for manipulation and re-rendering. But as humans, our understanding of the objects and scenes is also even a little more beyond that. So let's go back to this example of, we have seen input images, generalizing to a new object category for 3D shape reconstruction. You can do a little better with spherical maps, and you can do a little better with surfaces, back projections, and even better with spherical maps. But if you look at the top of the table again, you find that now it's already pretty smooth. But still, it just looks not right because we have such a strong prior that the top of the table should be round. But the output here is more like triangular, so that's not what we want. But if you look at the scene or look at the object from the input viewpoint, right? So the picture on the left, then you find that from the input viewpoint, it's already almost identical to the input image. So there's really not that much signal, right? It's almost impossible to discover that from the input image now because there's like really no much signal. So, but how are we humans able to do it? And we thought this is because we have such a strong prior that is shapes, especially man-made objects, they often have very abstract and program-like structure. In a case like the table in the bottom left, right? You can easily imagine there are 4 legs and they're identical, same length, but they also have a regular layout in this 2x2 grid, right? And also the bottom, they have 2 layers, and they must be identical as well. So to really capture this kind of prior, we have to go a little beyond from shape reconstruction to also shape abstraction. And I'm not going to go into detail into this paper because I want to talk more about scenes. But for people who are interested, we proposed this, we call shape domain specific language or shape DSL, and integrate it into a learning pipeline so that you can do inverse graphics or 3D shape geometry understanding, but not only in the space of voxels or meshes or point clouds, but you can reconstructing the shapes and projecting them back into this shape program space, which is defined by our shape domain specific language. And now, if you look at the top of the table, it just looks much better. At least aligns with our priors much better, that it should be round. Of course, by having more priors or domain-specific languages, you're also limiting your expressiveness. So if a shape is like so awkward, I've never seen before, and it has all those weird decorations that doesn't fit into the DSL, then your performance might be hurt, right? So there's always like a trade-off about how much priors you want to put into the system. Okay, this is joint work with Yonglong Qian, who is also a PhD student at MIT. So, our understanding of the 3D geometry is not only based on surfaces, but also, we have some priors of, there are parts, and the parts can be mostly regular, and there could be some like repetitions, like for loops and symmetry. And such a kind of priors not only exist in shapes, but I would say more importantly, they probably exist also in 3D scenes, right? So here's like a corridor, and you can see, the lights at the top are just repeating themselves, right? And the same in the middle picture. And if you look at the picture from the right, there is a building, and you can see such strong regularities on the windows and layouts of the scene. So these structures include, there are planes that are, planar, and also there are surfaces that are planar, and also there are a lot of symmetry going on, right? The symmetries and there are reflectional symmetries especially, and also repetitions, right? The lights are repeating themselves, the windows are repeating themselves. So we wonder if that's possible to leverage this kind of procedural priors or programs into our understanding of 3D scenes so that we can do, image manipulation, but not on the object-centric representation, but really on this leveraging these priors of procedures to do more efficient editing. Here is a demo. We use this Photoshop interface, but really it's not from Photoshop. It's a demo we built ourselves using our algorithm. So you can select the region and object of interest. And then ideally, the system can automatically figure out what's the repetitive units so that you can easily edit the scene and to make the building much taller or to make the building much wider. Right, so this is like our goal of how we want to leverage the priors of procedures or programs into image editing, into scene understanding. And eventually, of course, we also want to build that into Photoshop, but that hasn't happened yet. So we just use the Photoshop GUI to build a demo video ourselves. Okay, so our work in this line built on priors, they call it program synthesis for visual data, right? There has been some interest in, if I have observed image like this, I can probably use a program to represent that. The earlier work from Kevin Ellis et al. In US 2018, they do it on line joints, 2D line joints, where their approach is they first identify some elements, right, from 2D line joints, like lines and rectangles. And then going from lines and rectangles, they search for the programs. There are like latent programs, there are for loops. And then you can change the programs for extrapolation, so you can have more complex patterns. We also did some very preliminary work, I would say, back in actually 2019. That is for input. Now we do images, not only 2D, but 3D images, but synthetic, right? Because you can see it's synthetic and also pretty simple. So you have a number of images, and you first detect the objects, and you try to group them. And then for each group, you can infer the programs that explaining the groups as well as explaining the images. And you can generalize that a little bit to real images, where you can extrapolate the real images. You can see, okay, there's some programs explaining what's happening here. And then what if I change the program so that you can do image extrapolation by tying these inferred program representations with a GAN. Okay. So these are some very preliminary results, but it's so obvious that this is not good enough, because even for no matter for 2D line joints or for these simple 3D primitives, they're not close enough to the real pictures or natural images. So our goal is really to generalize to natural images. For example, for a picture like this, it's a milk and cereal. And there's, again, a regularity, right? But the regularity is so hard to explain. It's no longer line joints, lines and rectangles. It's not spheres or cubes anymore. It's these objects, which is hard to specify what's the shape of the cereal. So how can we do that? And the key idea we borrow is from the called internal learning or single image learning. And for people who are interested, I think this Zontag and Irani paper back in 2011 is very interesting. And the main idea is, the image statistics, they're often repeating themselves within a single image. It can be it can be within the same scale. You can see the patches of the roof are similar. It can be also across different scales, right? Because of perspective, right? You have the 3D scene, you perspective projected into a 2D image. So patches may be repeating themselves, but just at different scales, right? So how, and later, they also, okay. So built on this idea, later people have extended and integrated that with a neural network. So they say, okay, is that possible for neural networks to automatically discover these repeated patterns, right, from a single image? And their main idea is that the system is kind of complex, but the main idea at a high level is you can send an image into neural networks like AlexNet, for example, and you can pick the neural network activations. And then you can find, how these activations are likely to be repeating themselves at a certain displacement, right? So hopefully, by training on large image data sets, then AlexNet or those methods will be able to extract features that are more invariant to local small texture variations or noises, but being more robust and picking out the important structures. And by looking at how these activations are repeating themselves at a different replacements, you will be able to smartly and generalizably identify the repeated patterns, right? So we built on this idea, and then we apply something that's quite similar to this pipeline on this image, and this is what we can get. You can see, okay, the system smartly picked out the centroids of these individual repeating objects. And then you can do a program synthesis on top of it. But here you're no longer based on lines or spheres or cubes. You're based on these automatically extracted cues using deep networks. But then you synthesize a program on top of it. And the program now tells you, which part of the images are repeating themselves or similar objects. And using this program, you will be able to do things like imaging painting. Right? For example, if I have an image like this, where clearly there are a lot of patterns that are repeating themselves, and there's one patch that is missing. If I have this kind of program representation, I can first identify similar patches, and then I can search for a program that explains the centroids of these patches. And then for this missing patch, I will be able to identify other similar patterns, right? Other similar patches like those crosses. And then eventually we can send them into another neural network for painting. So this is what you can get with a program-guided representations for imaging painting, where you can see a cross is nicely painted. It's not really identical to any other crosses, but it does look natural. And it also captures the higher level structures like procedures within this image or scenes. You can do that for extrapolation. Again, right, you want to probably, if I add another row at the bottom, you probably want to add another row across this. Or for regularity editing, right? So in this example, I feel like, okay, the crosses are just on this regular grid. What if I want to make it a little more irregular? And this is what we can do very easily with this program representations. Here are some more results. In this serial example, you can do the same thing. What if I some patches are corrupted, I can inpaint it. I have such a strong prior that it should be triangular, so I should put another 0 instead of milk. And extrapolation, can I add another row or column of 0? As well as regularity editing, right? It's such a regular layout, but what if I just, make it a little more irregular, and how will the scene look like? Here are more results. Again, in painting, these are like a lot of the baselines, and these are the first 2 columns, the second and third column, they're not based on learning, and the other 3 columns, 4, 5, 6, are based on learning, and the 6th column is our output. You can compare that with the ground truth, right? It's interesting that these program or procedures really guide you in understanding scenes and in paint things that should be there much better with your intuition. Because to understand that, it probably requires a more holistic or global understanding of what really this picture is about, right? Instead of just getting local textures to make it right. Okay, so this is about how procedures and programs can help us understand 3D scenes. But if we think back, this looks like it's not really 3D. It's more about 2D scenes because everything now lies on a single plane. So for images like this, then we can see that there are like multiple planes, right? So is that possible to generate these programs into multiple planes, images with multiple planes? It is actually possible. So later we designed an approach to also describe images with multiple planes via a program. That is, of course, now you have to first set the camera positions. And then hopefully, which I'll explain later, you can come up with a way to segment the planes. And then for every plane, you will be able to explain what is inside the program with what is inside the plane with like a simple program, like a for loop, like the lights are repeating themselves. Okay, so when there's a single plane, we can just take AlexNet and take its activations and computing, how they're repeating themselves with different replacements. So this is like my bottom-up visual cues, which guide me into searching for the higher level programs. But when there are multiple planes, what are the visual cues we may use? One of them we'll say is vanishing point, because, if you have an image of multiple planes, then there is always a vanishing point and maybe 2. And the other is wireframes, right? Because the planes, they have to be connected to each other. So the wireframes are important signals of where these planes are. So we're exploring this bottom-up visual cues for visual program synthesis. Well, as we have seen for line drawings, people say, okay, let me first try to find the lines and rectangles. For simple geometric primitives, they'll say, okay, let's try to find spheres and cubes. And later, for single plane images, let's say we can use the repeated objects or repeated activations in AlexNet. And now for multi-plane images, the cues are vanishing points and wireframes. And we can, from the estimated wireframes and vanishing points, you can easily generate a number of candidate plane partitions. This is the vanishing point in the middle, and there are a lot of like wireframes, and then you can say, okay, how would I partition the scene into 4 planes, for example? And there are apparently a lot of candidates, but which one is correct? So our observation here is this is really a holistic process, right? The bottom-up direction, which are the correct planes, are also influenced by the top-down procedure, that is the program generation. So that is how, only if I can partition the planes correctly, I will be able to infer the program really well. So this is the main observation, right? So if we have 3 candidate partitions, I can say, okay, I just assume they are correct. And then for each partition, I can try to, rectify the planes. And then for every rectified plane, I can try to infer, okay, if this is really a correct plane, what is the regularity? If I want to infer the program on top of the plane, how would the program be like? So we're leveraging a very strong prior, that is, we build this, when humans build these models or buildings or any man-made objects, we try to make them regular. Right? This is our preference that we want to make things regular. So if you really correctly, you're able to correctly segment the planes and segment the planes, then you should be able to also infer a very good program on top of it. If your estimation or segmentation of the planes are incorrect, then it will be really hard to capture any regularity. And this is definitely not preferred. And only if you can segment the plane correctly, your regularity will be maximally kept. And then the program synthesizer will be able to best explain the plane or the pixels. So plane partition and program synthesis really help each other. And that's why we can use this queue to choose the middle one as our final candidate. So what's the benefit of having these multi-plane programs or procedures as an intermediate C representation for C understanding? That is, now you can do view synthesis, right? You can walk in this, we call it infinite corridor. Right? So if you don't have this program-like representations, you just build everything on pixels. This is a result from SingSing on the right, CVPR 2020. It's a very nice paper. It works also much more generally because they don't have this assumption. But for scenes that you do have this assumption, then if you just keep doing it at pixel level, auto-regressively, and everything gets much more blurry at the end. But if you have this program-like representations, and you can keep repeating the patches, using where I know that should be there, like lights, they should really be repeating themselves, and you can actually do much better in synthesizing or this like infinite corridors. You can also imagine how the scene will look like if I want you to move to look at the top left. Right, because now you have the 3D understanding, you have the program representations, you can do much better. You don't have to imagine out of the blue. As well as walking back, that's kind of similar to walking forward. You can walk backward, or you can look around. Right, you can turn around because you have this program representations. You understand, of course, any corridor cannot be really infinite, but you have a strong prior that there are planes and pieces, elements are repeating themselves, so you should be able to synthesize it. Well, for the baselines, it will be very hard for them to do anything. And similarly, you can do extrapolation. Right? This is what the demo we showed at the beginning. You have an input image, and then if you want to make the building taller, these are some baseline methods where they're more or less doing something, and some of them are really not bad. But again, because they don't have this object and repeating object representations and the notion, as well as the plane notion and the program, to explicitly represent the repetitions, you can still see some artifacts, while our method just do better. Okay, so to summarize, we talked about how we may connect 2D images to 3D shapes or 3D scenes, and eventually to some procedural representations about like the program-like structures in objects, in shapes, but also in scenes. And so here we're leveraging three important cues or notions from computer graphics: surfaces, objects, and procedures. And we've shown how these notions from computer graphics can help us, by integrating into learning systems, can help us to build learning systems that perform much better, but also much more general. Can generalize to NC objects to solve many hard problems like looking around. And the key innovations here is neural networks. We know they're so good at recognition, right? They can almost perfectly approximate a highly nonlinear complex functions like image classification. And also, for repeating objects, what are the repeating objects? I don't know. If I want to estimate the depths, what is the depth map? I don't know. It's so hard to explicitly write them down. So we're using neural networks to learn them. And on the other hand, we take domain knowledge for generalization. We take the notion of surfaces, projections, but also objects and procedures, and build into the system so that we can build systems that are much more general. So we should be very careful here, because it's very controversial to introduce any knowledge into learning systems. People always argue, okay, then that makes your system less general and more limited. But if there's no prior, you can really learn nothing, right? So there's just no free lunch theorem. So we have to build in some priors. How do you build the right priors? This is a very important subject, and we always try to understand. And it seems our suggestion here is you should build priors that are universal, right? Not building any priors that are very specific to a single scene, but build things that are really universal. Every object, they have a surface. There is 3D to 2D projection. You can see it from every image. Every image you take is projected from 3D. So you can take surfaces, and there's 3D to 2D projection. The scene or the world is made of objects, right? And there's regularity. So all of these general idea, if you can take them and smartly build them into learning systems with neural network for recognition, seems to really help you. And takeaway is we may want to think about, right, when we are seeing the images or videos, what are we really seeing? What is the causal structure behind the visual data? What makes we see the pixels as we see? There are objects, there's projection. Objects have textures, have surfaces. And these are really the things that make us see the visual data. So we should try to model what we can and model the universal stuff, and then let learning take up doing the things that we cannot do.